Hello! In this session, I'll demonstrate how the Bitdive platform works. We'll walk through system analysis, fixing identified issues, and validating those fixes using live runtime data. As our example, we'll use a simple microservices application, which is available on GitHub. You'll find the link in the description if you'd like to explore it yourself. The application is built with Spring Boot 3 and includes several microservices: OpenAI, Report, and Faculty. It also has supporting components such as Eureka, API Gateway, and Config Server. All of these are currently running in Docker containers. In the Bitdive interface, we can already see the service topology. Each microservice has been instrumented with the Bitdive library. The system is currently handling around 640 database queries per minute to Postgres. Let's switch to the HeatMap view. Here, we can see all microservices along with key runtime metrics, including HTTP requests, internal REST calls, SQL queries, schedulers, queues, and error counts. These metrics can be viewed at the service, class, or method level. By expanding our application view, we can see the individual microservices. We can also drill deeper into each service, starting from the controllers and going further down to specific classes and methods. I've already noticed that the report service shows a slower response time on the heat map. We can also identify a potential database bottleneck using the query count metric. The number of SQL queries is increasing steadily. Let's dig deeper and find out which method is generating this load. It appears to be the getStudents method. Now let's go even further and inspect the entire execution chain triggered within this method. By clicking on the method, we open the method tracing view where we can see all the calls that went through this method. Let's take a closer look at one of the traces. We can observe the incoming request as well as the input and output values passed through this method. Next, we see that it invokes the findAll method followed by a database call. In the SQL tab, we can see that a single request ends up triggering 165 individual queries to the database. We also have access to the full list of SQL queries executed within this call, along with complete data for analysis. As I mentioned earlier, the application we're analyzing is running in a local Docker environment. In parallel, I'm using JMeter to simulate load by calling various endpoints with predefined parameters, forming a realistic traffic pattern for runtime analysis. Let's switch over to Cursor, which is already connected to the Bitdive MCP server. We can see that the Bitdive library was added to the microservices, then the application was compiled and launched in Docker. Here we have the source code of the same microservices we've already seen: OpenAI, Report, and Faculty. Let's start with a high-level analysis of how the system behaves at runtime, not based on static code, but using live runtime data and distributed traces collected by Bitdive. To do that, I simply use natural language to ask Cursor to analyze the system state and identify potential issues. Cursor starts generating a response and determines that it needs to request data from Bitdive. We can see the first call to the MCP server. In this case, it fetches the heat map, which we've already reviewed visually. Cursor continues analyzing the system, making additional requests to the MCP server to retrieve data for specific services. It also decides to request a specific trace for deeper inspection. Let's wait for the full response to be generated. Now we can see that it has already identified several critical issues. Let's take a closer look. Yes, under critical findings, it mentions a SQL performance bottleneck and slow response time from the report service. We had already observed the same issues visually using the heat map. It also detects a potential N+1 query problem, which is likely the cause of the increased load on the database. Let's additionally ask it to analyze this method in more detail to confirm whether it really has an N+1 query issue. We can see that it sends requests to the Bitdive MCP server, which returns general information about the method's call chain, a specific trace as an example, and additional runtime data for analysis. Let's wait for the response to finish. And here it is, the N+1 problem has been confirmed. We now see a complete breakdown of what's happening at runtime in this part of the application, including all the executed queries and relevant data. It provides a clear and detailed root cause analysis along with specific recommendations on how to resolve the issue. Now let's ask Cursor to fix the N+1 problem based on the analysis it just performed. To do that, I include the code of the faculty microservice where the issue was detected directly in the prompt and describe the task in natural language. Thanks to the prior runtime analysis, the AI already understands the issue. It has full context, including the method call chain, involved components, and input-output values, which allows it to generate a fix with much higher accuracy than if it were working from static code alone. Moreover, it now knows exactly what to look for, what parts of the system are involved, and how data flows through the application. This enables the AI to propose a precise and reliable solution. Let's wait for the full response to be generated. Alright, it looks like everything is ready. The fix required only minimal changes to the code. I won't review them manually. Instead, we'll verify the correctness of the fix using Bitdive and Cursor within the next few minutes. So I'm accepting the suggested changes. Next, I'll recompile the faculty service with the updated code. I also need to remove the service from Docker, including its image, so that the updated version is loaded with the applied fix. Great, that part is done. Now let's run Docker Compose up again to bring up all the services with the updated changes. We'll wait a moment while the faculty service finishes starting. We can see the test running, and since the faculty service was previously down, some errors have appeared in the test results. Now, we're starting to see the first successful green requests, which means the faculty service is up and is handling traffic again. Let's switch back to the Bitdive interface and start by checking the changes visually. Returning to the service map, we can see errors in the faculty service. These are the same errors we observed during testing. Let's go to the HeatMap and inspect the updated method to see what's happening now. Right away, we notice that requests are being processed significantly faster. Let's take a look at one of the most recent traces. We can see that the method now returns a response that looks identical to the original one. At the same time, only two database queries are executed, one for students and one for teachers. The method itself returns a visually identical result. Now, let's move on to analysis and verification using AI and the Bitdive MCP server. I ask the AI through the cursor interface to verify that the fix was applied correctly by fetching the latest trace and validating the changes made. We can see that it first queries the Bitdive MCP server to get the identifier of the latest call, followed by a second request to retrieve the full trace data for that call. As we can see, the fix was applied successfully. This verification is based on the actual runtime behavior of the application. We can compare the results before and after the fix, and it's clear that performance has significantly improved with just a single change. Now, let's perform a more detailed contract validation. I ask the AI via Bitdive to make sure that all input and output parameters between methods are passed exactly as they were before the fix. This helps us confirm that the application logic hasn't changed, and that all data is returned in the expected format at each stage of the method call chain. The system understands the request and begins verifying all methods in the call chain along with their input and output parameters. To do this, it sends several queries to the Bitdive MCP server, retrieving both the prefix and postfix traces, as well as detailed information about each method involved in the call sequence. We can now see that contract verification is complete. The results include detailed data and a clear comparison table showing the behavior before and after the fix. As we can see, all contracts are fully respected. The fix appears to be working correctly. We also get a concise summary comparing the state before and after the changes. So, the issue has been detected, analyzed, fixed, and thoroughly verified using multiple methods, powered by Bitdive and AI tools. Excellent! We've now explored the full cycle, from detecting a performance issue to analyzing it in runtime, applying a targeted fix, and verifying the result using Bitdive and AI tools. What makes this process unique is the ability to work with real production context, live traces, input-output values, and method-level insights, not just static code. This allows for faster debugging, more accurate fixes, and better validation. Bitdive is designed to integrate naturally into your workflow, helping you reason about your system with clarity and confidence. If you're a solo developer or working on an open-source project, you can use Bitdive for free. To get started, just visit bitdive.io. Thank you for watching.